I'm good on that. But I'm still recording the class anyway. All right. Just like now, I started recording, and let me start with the agenda today. It's 11:07. The agenda for today's class is this math. Everyone can see that math. And this is a contact resistance math. It's something new that you'll be learning. In last class, you did one math, remember? Multiple layers, resistance, equivalent resistance. How you find the equivalent resistance in series? Just simply add them up and able to find the Q value. You did compare what? Sorry. This is a little funny, okay? So you did compare what? Like in an electrical circuit, Ohm's law. Everybody remember Ohm's law? Ohm's law is like V I R. The R is the same, electrical and what? Heat transfer. But this V is equivalent to what? Delta T. Very good, very good, very good. And this I is obviously the missing component Q, right? The Q. Okay. So that's for the series resistance. Now, if you are dealing with a contact resistance, what is contact resistance? What does it mean really? By the way, this is our main agenda, but not this is not all. I do have another agenda. I'm going to start with that because that's my main agenda. I'm going to start with that. I'll try to finish as much as possible. But I have another agenda to give you some hints on the homework. Homework 4. Homework 4, when is it due? Thursday? Okay. All right. So today we're going to talk about homework 4. Try to give you hints. Everybody started with that. Like last class, I did say about that, right? Everybody started with that. How many of you started with that? 1, 2, 3, 4, 5. Okay, others didn't start. Yeah, please start as that. And the reason I'm saying today we can address. Okay, those who started, please ask me a question. Okay, that's the thing for next time. Okay, and I'd like to upload another homework today, which would be relevant to it. I guess this contact resistance one, as well as there's some matrix going to come. Anyway, come back to the point. The contact resistance. Anybody heard about contact resistance before? Homework 4, we have a contact resistance of, oh, I'm sorry. Okay, the homework 5 is probably, okay, I remember now. Homework 5 is probably cylindrical coordinate system. This is the Cartesian coordinate system we're dealing with homework number 4. Okay, so what I was saying, contact resistance. Now, everybody, please pay attention. I'm trying to create a scenario so you can visualize what will happen today. So what we have here, stack of material, like some board, you can say, this is not a perfect one, the middle one, I don't like it. Yeah, now I like it. So, so maybe the strongest person in that class, whoever claims himself or herself as the strongest, and come here pushing so hard. Okay. So do you feel like in the intersection of these two plates or at the interface, okay, at the interface of these two plates, do you feel like whenever you come here and push it with your all forces, with all G power, do you feel like there will be any ER layer anymore? Or you can take out the ER layer? You know there is ER, right? In between this. What is that? In between? Mitch? Yeah, right? Yeah. So you're pushing it too hard. You feel like the ER layer you are completely wiped it out or still no. You can't. Why? Because I mean apparently naked eye you may claim it or it may appear that way, but you know in microscope always there are microscopic gaps, right? And this microscopic gap we're gonna do what? Keep the air, and the air is not a good conductor. You understand? Any solid is a good conductor. Gas is not like solid. Okay? This makes sense? So what it means, you are trying to transfer the heat. Okay? Mitch and Harley, please pay attention to me. So you're trying to transfer the heat from this side to this side. Equivalent to I is going from here to here. If we have a resistance because of the air much higher than this solid, then this I or Q will going to diminish. Does it make sense? The Q value is going to diminish, right? And that will going to reflected by that change of temperature or in current change of voltage. Does it make sense? So here and here, in heat transfer stays as long as there is a temperature difference, it will going to flow, right? So this change of temperature will going to interfere based on if you have a ER layer in between, okay? and that's the thing called contact resistance. There is a resistance that is happening in contact between these two surfaces. Make sense? Okay, and that is only here. Now, there is a remedy. If you are in a situation like that, how to resolve it? I mean, you do like to get the heat to transfer from one side to another side as soon as possible, as efficient as possible, right? What is the remedy? What do you think you can do to remedy that situation, like where the ERs are in microscopic gap? There is a thing called thermal paste. Anybody heard about it? Okay, so you can put some thermal paste. You can then still push it so hard, right? And those microscopic gap is going to filled out by some another solid. Okay, that's the thermal paste, and it could be very minimal, but it still is there. There's no longer any more air layer in between. That could be still here and there. Okay, but it can improve drastically the contact resistance situation. Okay, you understand the motivation of what we're doing now? So that's for contact resistance. Now, would be obviously, I mean, learn about the remedy and may do the math with the remedy, like the case kind of this and everything I said. But would like to see really that air layer, how much it can do the impact of the heat flow, right? We'd like to see. And this problem, when we're gonna do it, we may be able to see it, okay? Any question? You understand what you're doing today? Okay, let's start this problem formally. Everybody, please get your pen and paper ready. I'd like to see everybody take the class note. I keep my class somewhere. All right, so we have a problem here. By the way, you really don't need to write all of this. The reason I did told you, right? I did tell you, right? I in the Brightspace I did upload all the materials, right, for all the modules. Did you ever check? Anyone check? Brightspace, I have module 1 through module 4. This is module 4 going on. In module 4, you'll be seeing all the practice problem that I do here in class. And some additional problem is there with solution as well, right? So you can do, I did talk about it several times, right? I'm just trying to tell you, like, don't waste your time, like, write this problem. Everybody? Okay, just do the solution. Okay, but while I'm reading the problem, pay attention what is happening. So consider a plain composite wall that is composed of two material. I'm trying to highlight. Thermal conductivities for these two materials are given Ka and Kb. And the thickness is given as La and Lb. Okay, the contact resistance at the interface between two material is known to be that contact resistance value is given as 0.3 meter square multiplied Kelvin divided by W. Okay, the way people express the contact resistance is Tc. Okay, and you'd like to put this double prime on the top of that. You haven't seen double prime in last class, did you? Remember what you did? You find the R or resistance value for two different things. The convection and conduction. For conduction, it was what? L over Ka. For convection, it was 1 over Ha. Everybody remember that? We haven't seen the contact resistance yet, right? We don't apply any equation for contact resistance like before. For conduction or convection, we have this value usually given. We will be given with the value in your textbook. If you're going to flip through that chapter 3 most likely, yep, chapter 3 in both books, you would be seeing they have a table for contact resistance for different scenario. Okay, so again, so this is that one of the value that is given, and this R double prime Tc means that contact resistance is per unit area. And that should make sense as well, right? It's I kind of put my anchor here and explaining this thing again and again. The reason contact resistance concept, that once we understand the air layer and everything, how we can express it, right? Obviously, the resistance is the R. Now, why we bother to put double prime on the top of that? Why we bother to put per unit area? Your common sense should tell you, right? But the contact resistance for a particular situation, say like in this sandwich here for this two solid layer, right? That contact resistance that I'm claiming here, right? In the sandwich of this contact resistance. So this could be one unique situation, and you would be given with the contact resistance value. But here's the catch. You see, I now am showing these two plates which has some dimensions like the area I'm talking. Now, it may be only applicable if I'm going to give you the contact resistance for this particular place. It may be only applicable for this particular scenario, right? But it is not universal. To learn it, use it as a universal way, you may wanna use this contact resistance for per unit area. Does it make sense? Everybody understand? Per unit area, then it will be a universal thing. You understand? Then you can use it for any kind of math when you are dealing with like these two solid layer with whatever material it has, right? So that per unit length goes by this R double prime. Okay, hopefully everyone understand. If not, let me know. Okay, R double prime. Everyone understand why you have R double prime instead of R? It's a per unit area. All right, so let's start with the givens and then the contact resistance. I stopped here. Let me read through the problem again. So you have this material A adjoins at fluid 200 degrees Celsius and the H value is given. Material B adjoins with fluid 40 degrees Celsius and H value is given. What is the rate of heat transfer through the wall that is 2 meter high and 2.5 meter wide? Okay, and sketch the temperature distribution. Okay, so they have, let me now draw a quick sketch. So they have, in the problem, they gave you these two different layers, right? They gave you these two different layers where they gave you this side as 2 meter, so like this side as 2.5 meter, right? And then they said, okay, they said there's two plates, right? So there is the interface in between these two plates, and there is this contact resistance, right? And not only that, they said, okay, there is a fluid layer, right? And they gave you the temperature, say like T infinity 1, H1. They gave you the temperature T infinity 2, H2, right? And what else they gave you? They gave you the K value. Say like this is material A, this is B, Ka. They gave you Kb, okay? Anything else they gave you? Oh, they also gave you the thickness. So they gave you this thickness, La. They gave you this thickness, Lb. You will understand the sketch? You will draw the sketch? All right. All right. Now I'm gonna start to put things. So you have given with like this Ka, Kb, La, Lb, and the area which is 2 multiplied 2.5 meters square. So what are those values? The Ka is 0.1, this is 0.04, this is watt per meter Kelvin, this is watt per meter Kelvin. The thickness of those two things are 10 millimeter, which is, by the way, 0.01 meter, and then 20 millimeter, which is 0.02 meter. Okay, and then okay, so they gave you this T infinity 1, they gave you this T infinity 2. So they gave you T infinity 1 value as 200 degrees Celsius. They gave you T infinity 2 value as 40 degrees Celsius. Okay. What else? They gave you the H1 as 10 watt per meter square Kelvin, H2 as 20 watt per meter square Kelvin. And then second part, they say draw the temperature distribution or sketch the temperature distribution. Now, before I go on that, let me give you some time to write it down. So then they're asking you to find two things. First thing, they're asking you to find the value of the heat rate, right, through the wall, and then sketch, okay, thermal circuit. Okay, sketch thermal circuit. Um, so what are the assumptions? Anybody can give me some assumptions? Anyone? What are the assumptions? Steady state 1D. What else? Thank you. Yep, exactly those four assumptions. No heat generation. All right, Q dot is the heat generation. Do you remember Q dot is the heat generation? You have something on the phone? You have something on the phone? Don't class lecture. All right. So we understand so far the assumptions, the givens, engineering format almost done. Okay, sketch is done as well. Now it's time to explore. Now, obviously, you know this, right? This is called conductivity. At this point, everybody knows this conductivity, right? So there is no. And what is this H call at this point? Everybody knows this. H call what? Harley? Remember? Convective coefficient, right? All right. Anything else? Okay. I did capture the whole thing. Okay. Now, if I'm going to ask you that, I can draw it right away, but I would like you to do that. Okay. If I'm going to ask you, draw the thermal circuit, can you do that? It's kind of similar to what we've done in last class, right? So, first of all, identify the resistance. How many resistors there? 5. Thank you. Why? Would you have these two layers of solid and these two fluid layer, right? Is that so? That is your 4. What is the fifth one? The contact resistance, right? Right? See? So those 5 resistors that you have are like to one after another, so we can say that are in series, right? Everybody agree? One after another, so series. Can you draw the thermal circuit, all of you, based on the last class knowledge? I'd like to see that you can draw the thermal circuit where you have all 5 resistors, okay? And start to put as much info as you can on the thermal circuit. Don't just put some with the line and the what info that I'm referring here. Try to put the temperatures. Try to put the thermal resistance, right? For the solids, for those convection, you do know the thermal resistance. Remember, like for convection, you know it is 1 over HA, right? And for convection, you know it is L over KA, right? So try to put that, okay? Take your time. You haven't finished yet. So next 2 minutes, draw the thermal circuit. See if you can do that. Draw the thermal circuit where you would like to put the food. Draw the thermal circuit where you would like to put all the resistors. There are 5 of them, right? And all are in series, one after another. And you'd like to put, did you understand, right? Just draw the thermal resistance, and then you'd like to put as much info as possible. If I would be in your position, I'm going to start to put the temperatures on the thermal circuit, right? There are 2 different temperatures given. Now the question would be where those temperatures are. That is the important thing to understand, right? One temperature is outside here, another temperature is, I'm saying here, right? They said it's fluid, right? You can say it's here as well because we know this example is referring to here. Anyway, so one temperature is outside fluid. Let me correct myself. Another temperature is inside fluid, right? So you'd like to put them where? On the thermal circuit. That's something to think about it, okay? And then you have this all five resistance. And you'd like to put the equation for all five resistance. And as I give you the idea, the convection is 1 over HA. H is given, right? For the outside and inside. And conduction is 1 L over K. L for what? Solid layer A and solid layer B. That's LA and LB. Divided over Ka means Ka. Ka is kind of ironic, right? Ka is subscript A is referring to solid layer A. And then A again for area. Okay. And KVA, the same way. Then yeah, just finish it. Everybody finish it. Draw the circuit. Have you done it? Yeah, finish it. So you have, okay, yeah. So it is infinity 1 to infinity 2. And these resistance values that you have, you should be writing them, right? Do you need help? Okay. Where do you need help? Oh, you don't need help. I'm seeing here. And make sure L of K be A. You're missing A in the denominator. L of K be A. Ali, got it? You got it? What you do now? You didn't? Oh, you did. The last class we did learn this. Yeah. All of them are not serious. Okay. And then we have this temperature here, outside temperature T. And then we have this middle one, isn't it? Contact resistance member. Yeah. This here, say. And this one is for this here. This resistance, you can say it like R1. Okay. 1 over H1. H1 is here. Okay. Yeah. That's the equation. And this resistance is R2. Or you can say R2. And A. So that's the equation for the conduction. So contact resistance actually R. Oh, it does. Yeah. So you say that's R2. H2A. Alright, anybody have any question? Did you got it now? The questions?
I finished it over here. I'm just on the diagram.
Yeah. No, just draw the contact resistance. How do you draw the contact resistance? So you know when I'm saying contact resistance, just do
So double prime means
oh. Yeah. Now tell me what is the temperature here? Is it T infinity 1? Is it T infinity 2? Right? So you should be doing T infinity 1, T infinity 2, right? And then this is middle one for contact resistance, right? Yeah. So these are decided here. You have this H1 here. H2, right? And then this one is for the solid, which is right? And this one is for this solid. The RB for what? LB here. Alright. You guys have any question here? You guys got it? Have you got it? Yeah. Okay. Let me do it here. So everybody's in the same page. So actually, I'm gonna do part B first. Okay. Everybody see that? So this part B that I was saying, the thermal circuit resistance, which has, by the way, 5 resistance. I try to address individually to each student. Hopefully everybody got it. Let me know if you still have question.
and then you see these two temperatures given, right? Okay, and then say like this is your R1, this is your R2. Those are for convection, can be written as 1 over H1A, 1 over H2A. The middle one is RTC, right? The contact resistance. And say like this is for solid. A and B would be LA, KA, A. You see, L is A is a subscript here. Don't get confused with the A. So K, sorry, this one would be KB, LB, A. And this A that I'm writing next to KB or AB is the area. Okay, any question? All right, so that part is done for sure. And now just moving to so actually that part is not completely done. That is the fraction of that part is done, part B. The other thing that is asking here to find the temperature, say like this is TA, say like this is TC, say like this is TB. Everybody see what this temperature node that I am highlighting here? What does it mean? Everybody remember from last class? How do you remember from last class? We did explore different temperatures in between resistance, right? Okay, so these are these three temperatures. Now, the second part of the question is also asking, find this TA, TB, and TC. Isaac, can you find them? After I'm done, obviously everybody can find them. Steve, you can find them? Everybody can find them after 10 or 20 minutes, okay? All right, but everybody understand what is part B? Let's just focus on part A now, okay? On part A, if you remember, so part A, we are trying to find the Q, right? What is Q again? Heat rate, right? So we're trying to find the Q, and I don't know, it's not too important to do that. I'm gonna copy that and paste it here. Can you do that? Okay. I'm just trying to make it simpler, as simple as possible. Let's see if you understand. What I'm doing, Mitch, you are not here. Remember what I did here, this TAP, TB, and TC, I put them here. The reason is those temperatures are in between those two solids and the contact resistance. And the part B is asking, find the temperature distribution, sketch the temperature distribution. Referring means you have to find those temperatures. Okay, so that's part B. And in part A, what I'm doing, I copied the same picture, putting it here for part A, right? And take out this TA, TB, and TC. Why? Because I don't need them for part A. Part A is asking what? Finding the value of the Q, right? And this Q, we did talk about it, right? This Q is what? Just like first problem. Q is what? Is equivalent to I. Everybody remember the current, right? So this Q is I, right? Everybody is here except everybody was here in last class, right? Chelsea was not here, but other than that, everybody is here, right? You guys remember the Q was I? Matthew, remember that Q was I, right? You just said at the beginning, right? So then Q, can Q be found by using this equation? That same equation, right? Steve, we used it in last class. Isaac, you remember how to find the R total or total resistance in last class? What did you do in last class? You just add them, all of them. Do you know all of them? Not directly, but in the givens, the values are given. So can you find the value of the Q, Mitch? It should be, right?
You are given it all the values, like for R1, R2, RA, RB, right? Can you do that? Just try it. Give it a shot. I'm gonna help you. Yeah, try it. Give it a shot. You wanna try to find the value of the R1. Everybody, I'd like to see. You're trying to find the value of the R1. You're trying to find the value of the R2, RB, RA, and the equations are all here. Even I wrote it. You wrote it. You have it, right? And in the givens, all the values are there. Just have to be a little fast, okay? Just see as fast as you can do. So we have some time to talk about the homework things as well, right? So this problem, when you are doing, you want to do first. When I'm doing, I don't like to do first. Then you're not going to understand, okay? So you have your own control to do it first, okay? Try to find the value of the R1, R2, RA, RB, all of them. And then find the R total, okay? R total means just simply add them up, okay? Just try your best, okay? And as I said, I'm going to start writing shortly. So the thing is, if you want to do it by yourself, then only you're going to remember it, okay? It's not going to help you big time. If I'm doing it, you're copying it, not that much. But still learn. Then we are trying to find R total now. Our goal is to find the Q. And you see all the equations for the different R's are given. Once you have them, just simply add them up to find the R total, just like last class. Any luck with any of the R value out of all of them? Started? Okay. And I'm saying like do as fast as you can. Everyone. Just write it. Finish it within the next 2 minutes. See if you can do that. Find the R total. Let me give you the R total value. Maybe that can give you some motivation.
So I should have the R total value somewhere. So the R total value that I have, trying to separate them so there won't be any confusion, okay? So R total value that I have, which is by the way R1, R2, RTC, I don't know, maybe you want me to write it like in an orderly fashion, right? Maybe you are a very orderly guy or girls. So RB, R2, right? These all 5 resistance you're trying to write. Maybe you'd like to write them in terms of 1 over H1A. Okay, I think some of you already finished and want to see the value. It is 0.21 Kelvin per watt. Is that the value you found? Anybody found it yet? Somebody says yes. Oh, Logan, you found it? Nietzsche, you found it?
No.
Huh?
I said I got 0.45.
0.45. Am I doing some mistake? Maybe this is where you are doing. I didn't teach you guys. It's not your fault or not anybody's fault. I didn't teach you that. RTC is R double prime TC divided by A. Are you dividing this thing by A? Yeah, that's my fault. I didn't teach you yet, but I did imply it. Remember per unit area? I was making a big fuss. I was making a point about it, right? Why is per unit area? But that's the equation you might want to use, right? You want to divide it by A. Maybe you'd like to sit next to Chelsea.
I don't feel good, so I want to get rest.
Stick to it. It's alright. You got it? Anyone else? Yeah, this is just one distance. That's the contact distance. See, there's 2 solids are there. In between those 2 solids, there are air layers. Because of the air layer, there is another resistance. Okay, that's what called RTC. That's called contact resistance. Okay. That's the equation. The middle one, which means RTC. I wrote that equation, right? Did you see that? RTC double prime divided by A. Any luck with the value? 0.21. 0.21 Kelvin per watt. David, you got the value? Find the value. You got it, Amjad? Okay, those who are going a little faster, let me give the Q value for them. The Q value I do have is 762 kilowatt. Okay, David, you are done. David, I have a challenge task for you. Try to solve part B. Okay, you know the value of the Q. You know Q would be same for all the resistance, right? Logan, you might be done as well, right? So for the second part, listen, those Matthew might be done as well, right? Whoever done is you done also. So whoever is done with part A, okay, listen to me. You are done also part okay. So whoever done with part A, listen to me. For part B, what you're gonna do? You see that same Q is applicable for all the resistors. You know that, right? I did teach you that. So now, if you're trying to find, say like there's a temperature, TA, TB, TC. If you say like trying to find the TA, what you're gonna do? You're gonna isolate just one resistance. You're gonna isolate just one resistance, okay? And then once you isolate the one resistance, do you know the value of the Q for the resistance? You do. The idea here, for all 5 resistors, the Q is the same. Did you understand what I'm saying? All 5 resistors Q is the same, right? Now you can take consider just one layer. Just one layer. Say like that, layer, right? And then you have the resistance known for that layer, right? 1 over H1A. And then in one side, when the Q is going, the temperature is known as well, like T infinity to 1. The other side, after it hits the solid, you don't know the temperature TA, right? So what you're gonna do? You're gonna use that equation T is equal this T infinity 1 minus TA, right? Divided by only which resistance? R1. Only that resistance that I'm considering. There are 5 resistors, right? One layer, another layer, contact resistance, another layer, another real layer, right? So now you are considering only the one resistance now, okay? And your goal is to find one of the missing component, means the temperature. And you know the Q value that is going through all the resistance, and you know one of these temperature, and you know the resistance value as well. So what you're going to do? You're going to use the Q equation. Q equal to del T, which in this case, this T infinity 1 minus this unknown temperature TA divided by R, which in this case, just this R. Just the first resistance. Make sense? That's how you're going to find the value of what? The TA. Now here's the thing. Beauty of this thing. Once you have the TA value, the TC value, you can find it the same way. Does it make sense? The second resistance now we are talking. You know again another temperature, similar thing. You know the resistance, you know the Q, you don't know the temperature. For the other end, just use the same equation. Q equal, in this case, it would be TA minus TC divided by this RA. RA is the resistance. Okay? Now you have what? TC. Now you want to find the TB. Can you do the same way? So those who understand what I just explained, you should be able to finish part B as well. Don't worry, if you don't understand, I will be doing it, explaining it to you. You can copy and ask the question as well. Okay? Either way. RTC. So this is RTC double prime by A. You see that now, Chelsea?
Yeah.
Is better?
Yeah. I'm just not pretty sure.
Sorry, I just a little small.
Oh,
Alright, so
yeah, we'll do that. Yeah, all right.
and I have a feeling almost everyone got it what I said by seeing your face. Okay, if you understand what I said, you do it by your way, and I'm doing it as well. So if you are stuck at any point, just take a look what I'm doing. Okay, that could be helpful to you. Just so I don't like you to interfere what your thinking process, I'm not saying what I'm doing, okay? I'm just doing it silently, okay? So it won't hamper your thinking process. You'd like to do it by yourself, okay?
I got 3.02. Sure. Okay, so now.
So that part A. Anybody have any question with part A? Everybody done with part A? See, T infinity 1, T infinity 2. Three things I would like to highlight in part A. These two temperatures are given in terms of degrees Celsius. Now, when I'm trying to find the value of the Q, you see, I'm cancelling out the degrees Celsius with Kelvin. Anybody know the reason? Please remember, when you're dealing with change of temperature, that is same as change of Kelvin. Does it make sense? So this top numerator had degrees Celsius change of temperature. If you could have find the Kelvin for those two different temperatures and subtract them, you would have find the same change of temperature, because 273 you have to add for each of the temperature. 273 and 273 are gonna cancel out. Did you understand now? So that's why I can cancel out this change of degrees Celsius with the Kelvin. It's the same thing. In other words, I could have write the Kelvin. I didn't write it Kelvin over there in the numerator. Otherwise, you could have get confused how I'm doing it while I'm changing that, when I'm finding that difference or subtracting it from just the temperatures in degrees Celsius. The other thing I'd like to highlight, where in the right side I have the R total. I have K over W or Kelvin over Watt. How did I come up with this unit? Remember Q equal to del T over R, right? So if you are trying to find the unit of R should be del T over Q. Del T is K, Kelvin, and Q is Watt, right? So Kelvin over Watt. That's how I know our unit should be Kelvin over Watt, right? You got it? Now, the other way around could be, I'm doing a little shortcut here. Okay, the other standard way could be, you can start to plug the individual unit. For each of the parameters, like the H is watt per meter square Kelvin, A is meter square. So meter square, you're gonna cancel out. So you're gonna have a unit of Kelvin over watt. Okay. Just to understand the unit thing that I did, I'm just doing a little shortcut here. So that's the I would say like, oh, the cheating. At the same time, smart move. I'm putting a bracket and putting the unit all together at the end instead of dealing with individual. That way I'm still okay, right? I'm not like putting number with the units. In engineering, putting number with the units is a big blunder. If you start to do it in your job, then everybody will start questioning with your ability, like whether you have. Without units, never put a number anywhere in real life. You know that, right? The reason is the inch, mile, meter, kilometer, everything is different. Without units, if you are started to do that, you act like a high school student, not like a college graduate, okay? I hope at this point of your career, you already know this. Especially freshman year, I did emphasize this too many times. But here, still I'd like to emphasize it anyway. Anyway, part A is done. Everybody got this value? How many of you started getting part B value as well? You? Okay, I did explain part B, right? Let me give you some values first, so you have some motivation. So part B, we are doing part B. What I'll be doing for part B, I'm gonna simply copy this, and then I'm gonna paste it here. Okay, our goal is to find TA, TB, and TC. Let me give you those values of them first. So your TA should be, okay, answer.
Those who are little advanced. So TA should be 184.7 degrees Celsius. TC should be 169.5. Just 1 second. So you have this temperature, these. Oh, I'm missing something. There should be TD as well. Okay, there are 4 temperatures, right? So TB should be, let me rename them, by the way. I'm sorry. Let me rename them TB, TC this way. Okay. So TB should be that. TC should be 123.8 degrees Celsius. And TD should be, I don't have the value in my notes. That's something you got to find it. Okay. And the thermal circuit should be looking like, if I'm going to draw this, so I have this like T infinity 1, the temperature here, right? So like I have this T infinity 2, the temperature here. So this temperature usually goes flat unless it comes near the solid surface, right? And this temperature becomes like TA. And then you have this intersection here, right? So let me draw the intersection for contact resistance. This is the intersection for contact resistance, right? And in this is layer A, this is layer B. In layer A, what is happening? The temperature will gonna go like this, right? A straight line, but it is going down because the temperature will always go down. And then in the contact resistance, it will gonna go down here. So this would be your TB, and it will gonna go directly down. This would be TC, and then it will gonna go further down. This would be TD, and then it will gonna go down again until it hits the T infinity 2. And understanding this is so important, what I did. Okay, I did explain it verbally. Now I'm putting it in the sketch. Everyone understand this? Did you understand? In the contact resistance, there should be a temperature drop, right? Because that's the resistance anyway, right? Think this way. You put insulation in the wall, right? Everybody put insulation in the wall. What's the purpose of that? Just to put a barrier on the temperatures, right? If it's too cold outside, your goal is to keep warm inside. So that insulation is putting the barrier. Insulation is a resistance, by the way. Contact resistance is similar kind of resistance. So it creates a change of temperature. Okay, drastically. Make sense, Logan? See, it is not an efficient means of holding the temperature. Okay, because air compared to the solid, right? Air doesn't have a huge resistance compared to the solid. Solid doesn't have that much resistance, right? Yes. You know why I'm saying that? Solid can create resistance. Heat pass fairly, okay, easily. Anyway, everyone understand those different temperatures that I draw? Everyone understand why I'm doing it this way? Especially for the solid, you already understand. You did it in the first few weeks, right? Remember, it is like a straight line equation. Remember, del T is a straight line equation, del T over T. That's why it's a straight line in A and B. In between A and B, all I'm doing is thin layer, right? I'm just connecting them. But understanding the convection layer temperature is a little difficult. It's a little difficult, right? Because we haven't done something similar. So think this way, everyone. Everyone, please pay attention. Say like this is the air layer that I'm talking, right? What do you expect? The temperature of the air here and the temperature just next to the wall. Isn't it same? You understand what I'm saying? It's much easier to understand in this side of the wall. Today is still winter, right? Even though we are jumping to summer or summer/spring, but the outside is low, the temperature, right? So what happened really? That glass layer that you're seeing, when you're gonna touch it, you will be expecting most likely the temperature to be a little lower, right? On the glass layer. Everybody can expect that, right? But the air that here we're standing on, if I'm gonna stand here, Mitch, the temperature could be 70. If I'm gonna stand here, what could be the temperature, Chelsea, here? It's 70 still, right? So 70 here, until I'm running next to the window is almost 70. But here's the thing, when you go very near to the window, very near, you'll be starting to feel, oh, cold. And that's why this drastic temperature down. You see that? And your common sense tells you that, right? When you're gonna go close, very close to the window, you're gonna feel chilled, right? You won't be feeling chilling until very close to the window. So that's why you use straight line, the temperature same. You understand why that? Okay. So now that everybody understand everything, can you find the temperatures of TF, TB, and TC? Does it match with you, David? How many of you get any of these temperatures? Steve, David, Logan, anybody else? Get any temperature? No? Ali, you got any temperature? Ali, you got TA? Which one you got? Mitch, you got any temperature yet? You got one of them? Try one. Try to see if you can find one. Matt, you found anyone?
Not yet.
Not yet. Chelsea, you found any temperature?
No, because I'm confused at home.
You need some help?
Perhaps.
Okay, let me help you. All right, just focus on the just focus on the first resistance, okay?
Oh, I already did that.
So T infinity 1, I have this TA. What is this? So I'm writing this Q, and I'm saying this Q is the same Q as for all 5 resistors. Everybody understand that, right? Does everybody understand that? Why this is same Q? That is so important to understand. Okay, if that's the same Q, what is this resistance? Is it like R1, which is 1 over H1A? And then can I write this as Q equal T infinity 1 minus TA divided by R1? And can I write this TA? So T infinity 1 minus TA QR1. Can I write this as T infinity 1 minus QR1 equal to TA? Can I do that? I'm rearranging things before I start plugging the values, okay? There's a benefit of that. So T infinity 1 minus QR1, and then I'm going to start plugging the values. So what is my T infinity 1? Anyone? Is it 200? Minus, what is my Q value again? It is 762. What is my R1? 1 over, what is the H value? 10 and 5. See, I gotta make sure the units are consistent. Units are consistent, right? I have a doubt. I think this is what I did mistake. This should be 762 watt, not kilowatt.
Yeah, that's why I was confused here.
Yeah.
There doesn't need to be a exchange there.
Yeah, I did a mistake over there when I did the math here. For some reason I wrote kilowatt. This should be watt. Okay. If you're gonna plug it as a watt, then this is gonna match. Right, David? There's a unit mistake I did over there. So you should be finding the value of 184.76 degrees Celsius. That's your TA. Does it match with everyone? Okay. I'm sorry about this kilowatt thing, but
Did you got this? Did you find it? So now I want to not do any anymore. Okay. Now I expect you to finish TB, TC, TD, all of that, all of it. And we are actually running out of time. Bless you. What you wanna do actually, instead of finding all of them, find this is the first resistance. Because we have another agenda, just talk with the homework hints, right? So let's focus on David. You open the homework hints. I'm gonna work with you in person. David, Logan, if you have any question, Steve, you guys are done, right? You said 3 of you. Matt, you are done as well. Okay, so Matt, I mean, you open the homework question. I'm gonna entertain in person, and those who haven't finished it, please finish this one. So the second resistance you would like to do, on the second resistance, you wanna do this TA, TB, and you have this LA over KAA. This is Q. You wanna write this equation as TA minus TB LA KAA. Okay, and then you'd like to do this to find the value of TB, right? You wanna do it this way: Q multiplied LA KAA, and then you wanna do the KV by doing this math as like TA minus Q LA KAA. So I'm doing it for you actually. Now you gotta plug all the values to find the value of the second resistance. This way you wanna do the third resistance. Okay. And let me go in person and see. Everybody have the other answers, right? All the answers are here. I'm making it a little smaller so you have.
Find C before B?
Huh?
Are we supposed to find C before B? Because TB comes after the center of TC, right? So TC is here, isn't it?
Yeah, there is another one, TT.
Oh, TT.
Alright, so David, you have any question with the homework? If you don't have any question, you are done with that, you are good to go. You can go. Logan, you have any question with the homework? If you don't have any question, you are done with that, found everything. Then you have any question with the homework?
Same process.
Okay, alright. Did you find the value? Second temperature value, TB?
Yeah.
TB matches?
Yep.
So you are to find TC and TD as well at home. The next class only going to come, I'm going to check, okay? Everyone, I'm going to check. Next section. Next class only going to come, I'm going to check all the temperatures. You have any questions with the homework? You haven't checked. Do you have any questions with the homework? Okay, no. Well, yeah, the second, third problem. I'm sorry, the third problem is the parallel resistance, okay? Yeah, parallel resistance. I do have some hints for that. Yeah, the contact pressure 1 by that. So the fourth problem, by the way, you're gonna get the contact resistance value from the book. There is a table for that, okay? There is a table for that, and you're gonna get the value from the book, okay? And the third problem is the parallel resistance. Okay, parallel resistance, just use the thermal circuit parallel resistance. That's pretty much it. I do have more detailed hints if you are interested. If anybody needs help, let me know. I can send you detailed hints, okay?
And that homework is due Thursday.
That homework is due Thursday. Yep. So this is the help that I was saying, right? You see, for parallel resistance, everybody see that? And I'm putting it in record. So if you are watching the video lecture, you should have the access. Okay. So this is again, Matt. If you need help on problem number 3, I'm putting it in record. Okay. So this is in the video. I mean, it's on record. So maybe it could be helpful. Okay. Parallel resistance, how to work with that, the equation for parallel resistance and everything. Everybody, if anybody want it in person, let me know. I'm gonna send it to you as well. You too. You too.